to increase. Okay, so let's consider a system. Let's say that, for example, heads is how we want it to be. Okay, here is a system with one molecule. Yes. Okay, and let's talk about this room here. Okay, think about this room. A gas particle can be on that side of the room, or it can be on this side of the room. Can it be? Yeah? What's to prevent all of the particles from being on this side of the room? Now, I know you want to say, well, gee, the pressure would push it off that way, right? And indeed, if there was all the molecules were on this side of the room, there would be more pressure here, and they would go over there. But that's not to say it's not possible. It's possible. In fact, if we had one particle in this room, it would just be bouncing around, right? If we could see it, picture it bouncing around, yes? At any given interval of time, if I look at it, there's a vacuum on this side of the room 50% of the time, isn't there? That's because the particle's either over there or it's over here. If it's 50-50, half the time when we look at it, we've got a vacuum on this side of the room, right? Just like this guy, right? If I shake this thing up, 50-50 chance that I've got heads, right? Heads. Heads. Tails. Tails, right? So 50% of the time, there's a vacuum on this side of the room. What if I have two molecules, though? What are the odds that they're both going to be on that half of the room and there's going to be a vacuum on this half of the room? Yeah, it's 1 in 4, right? It's like heads, both tails. Both tails. What the hell? Okay. Heads, tails, right? There we go. Yeah, it's 1 in 4 probability that they're all going to be on that side of the room. Yeah? Because our states are both on this side, one on this side, one on that side, reverse of that, both on that side, correct? Only one of those is vacuum on this side, correct? What if I have 3 molecules? What is our likelihood that we'll find them all on this half of the room and none of them on this half? 1 in 8. Right? Shake this thing up. Nope. Then you can just keep going. It's like, nope. Oh, wait. Yes. Nope. There we go, right? There's our probability. What if I've got, how many do I have in here? 1, 2, 3, 4, 5, 6, 7, 8 coins in here. What's our probability? What's 2 to the 8th? What is it?
256.
Is it 256? Yeah, 1 in 256, right? And then the funny story is that years ago, right, I'm sitting there shaking this thing. If I got them all heads, I could shake this a lot, and it's just never, and I look down, and what is it? It's all heads. I took a picture of it. It's like, yeah, yeah. It's not all heads now, but there's only 2 tails in there, right? Okay. So think about this. If there's even eight particles, the odds are 1 in 256 that you'd have a vacuum on this side of the room. What if there's a mole of particles in here? 6 times 10 to the 23rd. Is it ever going to happen? I don't even, what is 2 raised to the 6 times 10 to the 23rd power? I don't even know, right? It's like, yeah? It's huge. It's a huge number. It's never going to happen, right? So the moral of the story is that if we have all the particles on one half of the room, that is a lack of entropy. That's a more orderly state. If we let them spread out throughout the room, that's more disorderly. We have less information. We don't know where the particles are. They're spread out over a greater area, right? It's sort of like all your stuff in your room. If they're spread out all over your room, that's more disorder. If they're all in one part of your room, that's less disorder, isn't it? In sort of a way, right? So if you think about this, if we had all the air in this half of the room and we opened that partition, isn't it likely that in ensuing periods of time after that some particles are going to go over there? And after a very short period of time, it'll be about 50-50, won't it be? Just because we're mixing it up, right? So it's not that it's impossible to make things more orderly, it's just that it's likely, and of course the likelihood is astronomically high if you have a lot of particles, right? Okay. Another way to say the second law is that heat flows from hot to cold. Okay? Heat flows from hot to cold. But again, this is the same thing, right? It's likely to become more disorderly. So entropy is disorder, right? And things tend to be more, it's a tendency to become more disorderly, right? More disorderly. Now we've seen this simulation, right? Let's just go back to it so that we know what we're talking about. Okay? So if we go in here, da-da-da-da, da-da-da-da. Okay, here's our disentropic state. All of these are 2s, all of these are 8s, correct? Yeah? Oh yeah, we can do full screen. Do you need the full screen? Yeah. I didn't know if you needed it, but if you need it, that's going to say, do you want me to remember? And I'll go, yeah. It never remembers. Just remember it. So there it is. Isn't this highly disentropic? This is very orderly. Disentropic as well, right? Yeah? So if your parents say, please clean up your bedroom, just say, oh, would you like it in a more disentropic state? Right? And they'll be like, yeah, whatever, or something like that, right? Okay. You know, do you deny confirming not wanting to not increase the entropy? Be like, I don't know. Right? Okay. And if we start to hit the space bar here, this thing starts to get mixed up. If we do this, it's going to be it's all jumbled up, isn't it? Now, is it impossible? Is it impossible? That is there a law against it going back to its original situation, all 2s and all 8s? Did I program that in? Like if you're almost there, don't allow it to ever go to that 2 and 8 state. Is that programmed in there? No, that's not programmed in there. But is it likely? No, not so much. If we had fewer particles, it would happen all the time. If we had 2, it'd be like it would happen 1 every 10 times or something like that, right? Okay, but we've got a lot. We've got 400 on one side, 400 on the other side. It's just not too likely to ever go back, is it? Okay, so don't you see that heat is flowing from the hot side to the cold side? Not because there's some magical magnet that makes heat flow from hot to cold, but because that's just the effect of averaging, of mixing it up. Doesn't that make sense? Yeah? So that's how this works, right? If you make it more disorderly, heat is going to have flowed from hot to cold. It's just like an averaging thing. Yeah? Yeah, yeah?
Does it become disentropic?
Becomes entropic, mixed up, all mixed up, right? Entropic means mixed up, right? Okay. So we'll go back. What am I doing? Let's go back to here. Is that a slideshow? Where's my slideshow? Is that it? Nope. It's like, ooh, all right. Thought we were showing that. Maybe I exited, right? How about this one? No device can turn all of a given amount of heat to work. How is that the same thing? You can't change Q, can't all turn into work. Why is that the same thing? Why can't I turn 5 joules of heat into 5 joules of work? Think about 5 joules of heat. What would it look like if you could see it? Bunch of moving particles. Are they moving all in the same direction? No, they're moving all in random directions at random speeds. They don't even have the same velocity, correct? Some are fast, some are slow, some are vibrating, some have potential energy because they've vibrated close together on their little bonds and they're about to move apart, right? It's pretty chaotic, isn't it? Yes? Now, let's turn that all into the kinetic energy of a juicy box of fruit, okay? Here's this juicy box of fruit, and this, we take 5 joules of heat and we give this 5 joules of kinetic energy. Think about that. Every particle in here is moving at a constant speed. Every particle is moving at the same speed, in the same direction, in a straight line, yes? Is that more disorder or less disorder? Far less disorder, correct? Oh, yeah. Okay, so we have reduced entropy. This is why this is the same thing, right? We can't do it, and the reason we can't do it is, well, because we violate this, right? We don't know why, but this just seems to be something that's enforced, right? Okay, the reason why in a heat engine you can't do it is that you always waste a little bit of heat, don't you? Yeah? You always waste a little bit of heat, and we just talked about that, right? Okay, let's hit the right arrow, okay? Systems tend to move toward more probable states. We just talked about that with the coins, didn't we? Right? Okay. If I've got these all heads up, right, is that a very likely state? No, it's far more likely that it's going to be mixed heads and tails. If I shake it, okay, it's going to become more disorderly, and it's also more likely that it will be disorderly, correct? They're the same thing? Yeah? Yes. All right. Let's say it another way. Oh, we already said this. All right. Heat flow, we've talked about this. Mixing of warm and cold water, yeah? Okay. Heat engines, yay. And then you can talk about processes. Let's talk about a plate falling from the table, right? If a plate falls from the table, the first